Alright, let's take a look at the definition of the horizontal asymptote and we'll look at an example of it. Okay, example 1 from the textbook will be used. The line y equals b is a horizontal asymptote of the graph of the function f of x if, okay, in terms of the limit notation, this is the meaning of the horizontal asymptote, if the limit of f of x is equal to b as the x value approaches infinity, or when the x value approaches negative infinity, the same condition holds true, then you're going to have the line y equals b as a horizontal asymptote. Okay, so let's take a look at an example of that. Okay, use graphs example 1. This is from page 70 of your textbook. Use graphs and tables to find limit of f of x to both directions, x approaching positive infinity and x approaching negative infinity. And with that, identify all horizontal asymptotes of the function f of x is equal to x over the square root of x squared plus 1. So on desmos, let's take a look at this function on desmos. Okay, this is what I have. Okay, so so I have that function, x over radical x squared plus 1. And if you look at this graph, even if I zoom out, as the x value is approaching positive infinity, your y value will not exceed 1. Okay, it is so close to 1 that desmos is rounding that y value to be 1. And on the other hand, if you're approaching negative infinity, then your y value will be very close to negative 1, that the desmos, the app is okay, estimating that value to be negative 1. So it's pretty safe. The pattern's not going to change anytime soon, if at all. So we could assume, for now, that the limits of this function f of x as x approaching positive infinity is 1, and the limits of f of x as x approaching negative infinity, on the other hand, is negative 1. Okay? The book doesn't cover this algebraically or analytically, depending on how you say it, but we'll see it. Okay, let's try to get the limit value using some algebraic manipulation. Okay, so on my next page, we'll do that. So here's the limit that we want to try to figure out. Limit of x over radical x squared plus 1 as the x value approaching positive infinity. There's a few things I want you to assume for now. Okay, something that we talked about intuitively. We don't have to prove this, okay, but you can see it graphically too. The fact that limit of 1 over x as x approaching infinity is equal to 0. And similarly, the limit of 1 over x squared as the x value getting really large, x value approaching infinity, is also 0. Okay, so we're going to assume these. It's safe to assume these. And what kind of manipulation can I do with this expression? There's a couple different ways to do this, but the fastest way that I found for this one is to divide the numerator and the denominator by x. So you divide the top part by x and you divide the bottom part by x. We want to be able to have fractions with the denominator being x when we're dealing with the infinity, dealing with the limits of infinity, because then we could somehow, okay, in hopes of getting to these situations, either ending up with 1 over x or 1 over x squared, or something similar to that. So let's see what we could do here. So our new numerator becomes x divided by x. Our denominator becomes the radical x squared plus 1 over x. And we're still finding the limit of this as the x is approaching positive infinity. And as you could guess, okay, there's nothing that's difficult about the numerator. X over x is just 1. But we have to do something about this. We have square root of x squared plus 1 divided by x. That doesn't simplify as it is. Okay, but we could change that by making x to be the square root of x squared. Okay, well that should make sense, right? X is equal to the square root of itself squared. Something like 3 being equal to the square root of 9. So why would I do that? So why would I rewrite the variable x as radical x squared. Okay, the reason for that is now I could divide those two square roots. Okay, when you have a square root divided by a square root. So let me just write about that part right there. So that becomes radical x squared plus 1 divided by x squared. They're both square roots, you're just dividing them, so you could put them as one quotient inside of the square root. And then in turn, okay, you have a fraction, but that you have a sum on the top. You have x squared plus 1 on the top. So you could split that up as x squared over x squared plus 1 over x squared. In turn, the x squares cancel out, and you end up with the square root of 1 over 1 plus 1 over x squared. So let me rewrite everything. Okay, so we were able to change this right here. We were able to simplify that, or I shouldn't say simplify, we were able to manipulate that to change to the square root of 1 plus 1 over x squared. And that's what I wanted, because then I could use this concept, the fact that the limit of 1 over x squared is equal to 0 when the x value approaches infinity. So let me rewrite this whole thing. So we got the 1 on the numerator, and then the new denominator that I got was the square root of 1 plus 1 over x squared. And then we're finding the limits of this as the limit as the x value is approaching infinity. And you could use the properties of limits to break this up if you want to, or okay, knowing the fact that 1 over x squared will be 0 as x is approaching infinity, your final answer will be 1 over radical 1, which is equal to 1. So that is consistent with the answer that we got with desmos.